Thank you, Vilna. When we think of a MagSafe on a diamond plant, our mind immediately goes to the DMS circuit. We know that in a DMS circuit, we use a magnetic separator to recover the medium. And in the diamond application, Fezzi is used as a medium, a very expensive medium at that. DMS MagSafes have been designed and perfected over many years to effectively and efficiently recover your medium. However, as with most separation equipment, there's only a certain degree of differentiation that can occur, i.e. magnetic and non-magnetic. And in our DMS circuit, ideally we should be recovering Fezzi. But what is this? Is your magnetic separator recovering the right magnetic medium? If we take a closer look at the ore that is mined and processed on a diamond plant, the most common ore that diamonds are associated with is kimberlite. Now, there is an emphasis on associated. Kimberlite ore is only a carrier. Where there are diamonds, you are likely to find kimberlite, placer, or lamperite. However, where you find these ores, you will not necessarily find diamonds. Diamonds form in the Earth's upper mantle just beneath the crust, whereas kimberlite, placer, and lamperite form deeper within the mantle, closer to the core. These ores get pushed to the surface through volcanic eruptions. Now, they aren't called eruptions for nothing. This is a turbulent journey, and they pass by the diamonds, dragging them along to the Earth's surface. Now, imagine you're minding your own business, standing on the sidewalk, and then suddenly from behind, a group of people come rushing by, and one of them just grabs you and drags you along. You don't know where they're going, but you are going with. Next time something like that happens to you, just think to yourself, it's okay, at least I am a diamond, even if it is just in the rough. The picture shown is a world map of known diamond producers marked in yellow, and also known kimberlite, placer, and lamperite deposits. It is important to note that there are some countries where there are ore deposits where diamond mining is not happening. And especially in South Africa, ilmenite, calcite, and magnetite. Now, here is our little problem. What do we know about magnetite? Quite a bit actually. But most importantly, it is a ferrous-containing material that is ferromagnetic and is used on DMS plants as a separation medium. Can we see that this might cause some problems, especially if the medium that we are using on our plants is Fezzi and not magnetite? Now, what happens when you have magnetite in your Fezzi DMS? Through the process of the ore preparation for a DMS circuit, we use mills and or scrubbers in an attempt to liberate the diamonds from these non-essential ores. In this process, we reduce the top size of these particles and break them down, some of them even becoming fine enough to pass through your drain and rinse screen to report with the Fezzi to your DMS magnetic separator. When the magnetite is introduced to the DMS magnetic separator, it will be recovered. But why is that? The graph shown is for a Multotec Permax unit, and it indicates the magnetic field intensity as 2000 Gauss on the drum surface, and it becomes lower as we move away, down to 600 Gauss at 50 millimeters from the drum surface at the bottom of your separator tank. Now, because magnetite is a ferromagnetic material, it can easily be recovered within this range of magnetic field intensities, and it will be recovered together with your Fezzi. But what does it mean to have the magnetite recovered? Magnetite SG is lower than that of Fezzi, and a DMS plant is operated based on density. The medium to ore ratio is carefully determined during the process design stages, giving a very specific operating density to ensure the optimal cut point in your DMS cyclone. Adding magnetite with a lower SG to your medium will cause it to become a contaminant over your recirculating medium, and it can lower that density. So, how do we approach this problem? Prevention or correction? Prevention is always better than correction. because you don't correct just once, you don't correct twice. It is a continuous process. So let's approach prevention. If our problem is the material reporting to the magnetic portion of the separator, why not just use a magnetic separator? However, as we are trying to prevent the magnetite from contaminating our FESI, we have to remove this ore prior to the DMS. And as the process is fairly dry prior to our DMS circuit, we have two options, an overbelt magnet or a dry drum magnet. Firstly, let's look at an overbelt magnet. The most common use of an overbelt magnet is for the removal of tramp metal ions. These units are usually electromagnetic units, and they have an intensity of around 2,500 to 3,200 Gauss. They are installed at plus minus 200 to 500 millimeters from your conveyor belt surface and require cooling due to the heat generation of the electromagnet. However, a little unknown use of an overbelt unit is for the installation for ore beneficiation purposes, especially in the diamond applications, where they utilize permanent magnets that has a lower power consumption. These units can be installed closer to the belt as they have a high magnetic gradient, and these units utilize rare earth magnets that have an intensity of 600 to 700 Gauss at 200 millimeters from the magnet surface. These units can be installed in either an inline configuration at the head pulley of the conveyor or in a cross-belt configuration along the length of the conveyor. Some advantages of these units are that they have permanent magnets. They can be easily installed in an existing plant, especially when utilizing the cross-belt configuration. However, a disadvantage is that they can not easily recover those fine particles. As with the movement of the material on your conveyor belt, these fines tend to migrate to the bottom of the conveyor. Next, we look at a dry drum magnetic separator. This unit utilizes permanent magnets that can be either low intensity or medium intensity, up to 6,500 Gauss on the drum surface. It has a working distance of up to 80 millimeters and utilizes a vibratory feeder. A dry drum unit does not only utilize the magnetic properties of an ore for separation, but also utilizes inertia. As you can see, we have three product lines, a tails, non-magnetics, a mid-links, semi-magnetic, and a magnetic concentrate. If the magnet intensity utilized within the drum is low, and you have a large particle that is magnetic being introduced onto your drum surface, you can have the inertial forces that is trying to fling the particle from your drum surface being larger than that of the magnetic force attraction trying to keep the particle on the drum. And that can cause some of your magnetic material actually reporting to the tailings. For our applications, however, the tails will actually be our product as we are trying to get rid of the magnetite that is magnetic. This unit especially can easily recover your fine magnetic particles as the inertial forces on these particles are a lot less. That is one of the advantages of a dry drum unit. A disadvantage, however, is that brownfield installation for these units can be a bit difficult and they need to be planned for a new installation, ideally. So now we have looked at these two units that we can install, but is it even really worth it? Let's look at a case study right here in Southern Africa. Multotec had a client that noticed some larger particles reporting to the overdents in their DMS circuit. An investigation was done, and it was determined that these oversized particles were actually all fines. These fines have started to accumulate within the DMS circuit and actually started to affect the correct medium density. The density was affected to such an extent that the client had to purge the entire medium once every 3 to 12 weeks. And this costed them round about 300,000 Rand every time. Now we can all know the order in which these notes are brought up is not the order in which they were noticed. The first thing you notice is the 300,000 Rand that you have to spend once every quarter or even more frequently. Thus, the client approached Multotec and asked us to assist with removing these ore fines. After a site visit, it was noted that even when using a small, low-intensity handheld magnet, there is a significant amount of magnetic material within the feed to the DMS, and test work would be required for optimal recovery of this magnetic material. Test work proposal was compiled, and it was decided to do dry drum MIMS test work on the DMS feed, DMS concentrate, and the tailings. An analysis on all three streams was done, as received from the plant, where it was seen that within the feed, the magnetite content was 0.66, with 0.24 within the tailings and 1.11% within the concentrate. Unfortunately, for this test work, we were not privy to the complete process information on site. However, if we use a typical cyclone split across a DMS cyclone of 98:2 for the float in the sinks, our theoretical magnetite content in the feed should have been 0.26 if we look at the DMS concentrate and the tailings magnetite grades that we measured. However, the actual measured grade in the feed was 0.66, indicating that somewhere in our process we have a magnetite accumulation. If we take an example of a process that has 100 tons per hour feed to the DMS circuit, that is an accumulation of 400 kilograms of magnetite per hour. If we have a typical 6:1 Fe to ore ratio, we will have 600 tons of Fe within our recirculating medium, which will have at 0 operating hours an SG of 6.7. After operating for 1 hour and a 400 kilogram magnetite accumulation, our SG would have been brought down to 6.69, which is still basically 6.7. However, after 24 hours of operation, it is down to 6.67. After 1 week of operation, we are down to 6.54. And after 3 weeks of operation, we are down to 6.32. This will start affecting the cut point on your cyclone if this DMS density is not fixed. Next, the graph shows the mass splits that we have achieved across your magnetic separator to the magnetic and the non-magnetic fractions. In our DMS feed, we were able to recover 10% of the material to the magnetics portion, with the tails and the concentrate only recovering around 7%. However, if we look at the magnetite recovery, in the feed, we recovered 97% of the magnetite to the magnetic portion. Only 35% was recovered in the magnetics and 100% was recovered in your concentrate. But we know we want to prevent, not correct. There is no use in removing 100% of the magnetite from the concentrate if you are still contaminating your Fe. So what did we see in our test work? We saw that adding a magnetic separator to your DMS feed provided very fruitful recovery for your magnetite. This prevented the magnetite from actually contaminating your DMS circuit. And the prevention of contamination can save you up to 300,000 Rand or more on Fe consumption per quarter. Depending on the size of your plant and the type of ore that you are mining, a dry drum magnetic separator can cost you around 1.5 million Rand. Thus, playing it off against the 300,000 Rand we need to spend once every 3 to 12 weeks, we can pay off our dry drum unit in about a year or even as little as 4 months. And after that, we will only be saving money. Now, when we are thinking about a magnetic separator on a diamond plant, you might not have been thinking about a dry drum magnetic separator, but I promise you, it's worthy to think about. Thank you very much.